Afternoon, everyone. And I am hoping that I'm actually streaming right now because my OBS software is doing something weird that I've never seen it do before. So let me go ahead and verify things are going good on your side of the stream, and if so, we can go ahead and continue. I'm gonna see if this works out. Okay, I'm seeing myself. So things are good. All right. So guys, welcome to another stream of CosmoQuest Astro 101. I am your host, Dr. Matthew Richardson. And today, well, overall, my plan is to talk about the fate of the universe. But before talking about the possible fates of the universe, I plan today to primarily focus on a related topic to the fate of the universe, and that is the geometry of the universe. So, pop out the chat so I can be able to see comments a little bit easier here. Get rid of that screen. Perfect. All right. So, yeah, Phoenix, you're getting to it right now. The heat death and some other top possible fates for the universe, but we're not going to talk about those just quite yet today. We're going to talk about the geometry because the geometry is, of course, tied into the topics such as like heat death or the big crunch and stuff like that. But today we're focusing on the geometry. And so this is probably going to be a relatively smaller discussion, or small and short in time, that is. Friday we'll probably have a much longer discussion with a few problems that I'm currently working on to be able to present during that discussion. But we're talking about geometry. So first things first. Well, what are the possible geometries that we could have for the universe? And the possible geometries are what we kind of see here. So if we could imagine, of course, the universe, the early universe starts off like pretty much as a singular point. Everything that composes the universe is pretty much within that singular point, and then we have that big explosion, right? And from that big explosion, we start to get some sort of shape for the universe. And those different types of shapes that we can get are what we see here. Where starting from the left going towards the right, we kind of begin with the fact that we can either have a spherical shaped universe, or we could have a flat universe. And lastly, I mean, the names are different, but I'm putting the common names that are used. We could have an open universe, or as they put here, negatively curved universe, which I'm not going to get into, but we can have an open universe where, in the case of a spherical universe, the shape is spherical, flat like a sheet of paper. Or if it's open, it has what's known as a hyperbolic geometry to it. Now, these particular shapes for the universe, or geometries for the universe, are heavily dependent upon one thing. And that's what I'm primarily going to be focusing on for our discussion. That one thing being the density of the universe. So again, guys, this is going to be a very short discussion, and you're more than welcome to add on to it and ask questions as I talk, and I'll try to catch the comments and questions as I move along. And so, to understand these different possible shapes for the universe, we need to understand this one thing known as the density parameter. It's a part of cosmology. Density parameter omega. And so my easiest way of being able to explain what this density parameter is just basically to show the equation for it. So what we're looking at here is the density parameter omega, which is on the left-hand side of the equation. And we see that it's equal to some other things that look similar to it, of course. Will have the same units, which in itself, it's unitless. But the key thing about the density parameter is that it's a ratio. And it shows the ratio in the box underneath the left-hand variable, or the variable on the far left-hand side, as basically some density divided by some essentially called a critical density. So the density that's going to be in the numerator is the density of the actual universe. This is the density that you can physically measure for that's based off of a few things, which I'll get to in a second. But the key important thing to all of this is the critical density. Now, this particular density is theoretical. And it's what ultimately determines whether or not ultimately determines the shape of our universe. The critical density will allow us to be able to determine whether or not the universe is either closed, which if it's closed, it would take on that spherical shape that I showed earlier. If it's flat, take on the flat shape that I showed earlier, or if it's open, which is the hyperbolic shape. Now, this density parameter omega is dependent upon us being able to determine a few things through observations about our universe. One of those things being, which denoted here is omega m, corresponds to the physical matter in our universe. And that matter being a composition of two things, actually. The ordinary matter that we call baryonic matter, or as we probably know as like protons, neutrons, electrons. This particular type of matter, or is the physical matter that or the ordinary matter that we're able to see in our universe. And the other type of matter would be dark matter, which is the matter that we know very little about. But we know that it's there because of its gravitational interactions with ordinary matter. The other density parameter, or other density that's going to be important in being able to determine the total density, is this density parameter known as the relativistic or the density corresponding to matter. I'm using this word very loosely here. Matter that corresponds to like relativistically moving particles. I'm trying to be very careful in saying this because this particular term is composed of for example, as it states here, light, which in itself is not matter because it doesn't have mass, but light has momentum though, so it has an effective mass. And neutrinos, which for the most part we've been able to measure, does have mass, but it's very, very small. And then lastly, the last parameter that's going to be important for in determining the total density parameter is the one that actually that plays the major role, at least now, plays a major role in the density parameter. Is going to be the density term that corresponds to dark energy. And so this particular term, of course, is going to show up like in cosmological models as the cosmological constant omega, or lambda, excuse me. And it's the collection of these different elements of our universe that come together to be able to give us a total density. So, as I stated earlier, this is going to be a very small discussion, and mostly because of the fact that I'm working on problems right now to be able to give a more, I guess, mathematical sense of how we can be able to use this information. But together, these come together to end up giving us our total density and help us be able to better understand the shape of our universe. I'm going to quickly take a moment to look at comments. So to answer Hanny's question about why are these things separated out in this way. So whenever you're talking about the total density of our universe, typically what comes to mind whenever you're talking about density, of course, is mass per unit volume. And when you think about mass, of course you think about just normal matter. But there are things though that affects our mass in our universe. Of course, the mass itself is going to be important as far as calculating the density, but other things that kind of have like a mass equivalence would be like, for example, dark matter, which of course we can't physically measure. We can't physically detect it directly, but we know that it's there because of how it interacts with ordinary matter through gravitation. Then of course you have, like, for example, light and neutrinos. Neutrinos have mass to them, but for example, light doesn't necessarily have mass, but it does have an effective mass because it's able to affect matter, by changing its momentum in its interactions. And then, of course, we have dark energy. Now, dark energy, just like dark matter, we know very little about, but we can detect its presence because of the fact that the universe is undergoing expansion. In comparing the composition of the universe now relative to how it was in the past, you can be able to see that the universe's composition, and I wish I could just quickly pull up like a diagram that would show its composition. But in the past, like I'm talking more so about hundreds of thousand years after the Big Bang, the composition of the universe was much different than how it is today. In fact, if I'm not mistaken, back then, dark energy didn't really play a major role in the universe's composition. The composition was primarily composed of, for example, like radiation and ordinary matter that we know of. But now the composition of the universe is very much different. In this case, taking this equation for example, um, our omega lambda term is the term that dominates the density parameter, and that it takes up roughly 70%. Well, I think it's around 70% of the overall total density. And then the other ones play then the dark matter or the omega m term would correspond to roughly around 30%, and then the omega relative or relativistic term corresponds to something that's less than 1%. But yeah, they separate out because they each have different contributions to this total density parameter. I have not been able to listen to Dr. Alan Guth. I hope I pronounced his name correctly. I haven't been able to see that. Haven't been able to hear information from him about the topic. I will definitely check it out though. Um, so Hanny asks, what is the P and P sub C? Well, in this situation, the P or the rho corresponds to the density measurement, the actual density measurement of our universe. Rho sub C is what ultimately determines the geometry of our universe. I think right now it currently, well, no, let me not even say that the current value because I don't want to get it wrong. But I think it's like somewhere in the order of 10 to the negative 26, I think, grams per cubic centimeter, maybe something like that. But that erosive C is really what ultimately will determine or helps us being able to establish a threshold of what would allow us to understand what the shape of the universe is. So if the rho term or rho is equivalent to rho sub c, that means that we have a flat universe, and ultimately what that means is that our universe will at some point um, in the future will eventually it will stop expanding and it becomes stationary. Um, if the rho term is less than rho sub c, and I mean, I have one more slide to show, and it gives a much clearer picture. But if the rho term is less than rho sub c, that is, the actual density of our universe is less than the um, the critical density calculation, then so mass is less. That means that our universe is going to be open and it'll just continue to expand forever. Now, the rate of the expansion is going to be heavily dependent upon the the um, the dark energy term. And then lastly, I think the other condition would be if the density, actual density of our universe, if it's greater than the critical density, then you get the situation that the universe is going to be closed. Um, and then there are some theories as to what happens with the closed universe. Eventually, the universe should go back. Um, well, I'm gonna save that for another discussion, but yeah, if it's closed, it takes on the spherical shape. If it's open, it takes on that hyperbolic shape. If it's flat, then it's flat. And there's a reason why I'm not going too deep into this because, like I said earlier, I'm working on a few equations or some problems, and I want to be able to present those problems along with along with that information that I was just getting ready to talk about. All right. So lastly, and like I said, this is a very short conversation on the fate of our universe. More so talking about its geometry. Um, with the future stream, we're going to talk about how that geometry plays into the possible different fates. But I kind of was getting to this already, and that is that with this density parameter, you're able to relate it to the geometry of the universe. Where, as I was already saying, and this is just basically saying it another way, if the total density parameter is less than 1, you get well, lower density corresponds to an open universe. It takes on that hyperbolic geometry. If the if the total density is equal to 1, that corresponds, of course, to the actual density equaling to the critical density, which, if I'm not mistaken, some measurements now actually support this particular theory for the geometry of our universe, and that is that the universe is more than likely flat. And of course, if you get the situation that the density parameter is greater than 1, which corresponds to the actual density being greater than the critical density, you get a situation that the universe, it takes on a spherical shape and is closed. And guys, that's pretty much it for my discussion today. Um, this particular discussion lasted about 15 minutes. I didn't think it would take a very long time to go over it. Always open and closed at 11. Yeah, that is definitely a lie. Not always open, but it's an interesting name to use for a sandwich shop. See, the thing about it is that now I'm kind of going into the discussion I want to have, and I plan on having this discussion on Friday, along with the problems I've been working, or the one problem I've been working. Um, so if we do have a an open universe. So if we have a closed universe, um, there is the one particular fate that's associated with that is the Big Crunch. I'm not going to get much into it right now, but if you want, you're free to look it up. Um, but if we have an open universe, there's a few theories as to what could happen, to us. Of course, we won't be around. This will take a great deal of time for any of these predictions to come true. But an open universe could lead to other types of possibilities. Oh, which one do I prefer personally? Um, well, personally, I mean, I would go with a flat universe if I could choose, just based off of what I know about about what these shapes mean, as far as the what will happen when the universe ends, essentially. Um, I'd prefer a flat universe. So yeah, with the information that we have so far, I think there's evidence that would support the idea that we currently have a flat universe. And if I'm not mistaken, this is based off of I think I read that it's based off of measurements made by WMAP of the CMB that supports the idea that we currently live or our universe is currently flat, which is, which is quite amazing because, That means we'd have to have an actual density for our universes exactly, or very close to equaling, or not even very close, actually equal to the critical density value. So yeah, elliptical galaxies are not flat, but this particular this concept is more so related to the overall shape of the universe. Not anything that's happening on like scales of galactic scales, but more so like on really like large like cosmological scales. Beyond that of the observable universe, I mean the universe as a whole is what this concept is related to. Yeah, for the most part, I mean galaxies themselves, aren't undergoing expansion. I mean, when you're talking about expansion, you're generally talking about the physical distance like that's occurring between galaxies. But yeah, guys, I mean, this is what I wanted to talk about today. By all means, if you ask questions, I will answer the questions, and I'm going to try my best not to answer them in too great of a like too not too deep, because I will be talking more about this on Friday, where we'll get into topics like the big crunch, and I think it's heat death, the big freeze. So so inflation, if I'm not mistaken, is more so dealing like with the early universe, right? And I don't think that particular topic deals primarily with like the density of the universe and how the actual density relates to the critical density. And you know what? I want to be actually be sure because I don't want to be saying something that's completely wrong. Yeah, this is right. I honestly just did a really quick like I typed in inflation cosmology into Google, and based off of what I'm seeing here, right? That's not this particular concept isn't really what ultimately determines. I don't think we have to actually talk a great deal about cosmic inflation in relation to in relation to the geometry of the universe. Wait a second. I call it Falcon epicycles. And so, I mean, guys, that's pretty much all that I wanted to discuss. Oh, wait. You're talking about a different type of inflation. Well, this is definitely something I'm going to need to add to our discussion on Friday. Huh, okay. Thanks, Larry. I honestly hadn't seen that. No, no, we don't. We don't want to talk about it. Hey, and Locks. I don't want to mispronounce that. All right, guys. Well, that's pretty much all I have for today. Again, we will be continuing this conversation on Friday, along with the problem that I'm currently working on. Oh, no, 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 no problem, Larry. By all means, if you guys have like comments, questions, bring them up. It makes for a far more interesting conversation. All right, guys. Well, that's it for today. I will be back after Daily Space on Friday, and I look forward to seeing you guys then. All right. Okay, bye, guys.